Hello again, this is Al from Al's Tutorial Lessons, and this is my new logo. I hope you like it. I didn't actually make it all myself. In fact, I made the N and the O. So I had intended to put the lesson title in this box here, but I don't have enough letters yet, so I can't do that. So I'm hoping you're happy with this little introductory screen. This here is Snoopy. That's another possible intro screen. Anyway, I like this one for now. Now, I've been sitting here trying to do the impossible, and I've given up trying to do the impossible. I need to explain 2 Intel instructions to you before going on. And it simply cannot be done in less than 20 minutes. So, and I promised that we were going to get to this parsing the command line thing in, well, I think I've been promising that for about 5 lessons now. So I want to get to that and get through that in this lesson. So it's just going to take as long as it takes. Maybe an hour, maybe it'll take 2 hours, but we're going to get through it. And I'm not going to quit till we're done stepping through at least one iteration of the parsing. Now, the 2 commands that I've got to show you are ones that I use quite often, so if you didn't know how they work, the code wouldn't make very much sense. They are useful commands, very useful commands, or instructions I should say. It's the proper word. And I'm going to show you down here on the bottom. The ones I want to look at, just 2. Well, two involving this rep. Now, rep here by itself is not an instruction. It doesn't do anything. This is a prefix that goes before certain instructions and causes the processor to repeat doing whatever the instruction is on the basis of some condition. And here's what I got out of the help file. Repeats the execution of a string instruction. Now that has a special meaning. A string. What is a string? A string, if you want to give it a definition, would be a contiguous block of memory containing elements. So essentially a string is an array of either bytes or double bytes, which are called words, or double words, which are called double words. And it keeps repeating the instruction. So this thing, when an instruction is prefixed by this rep, that instruction will continue going on, being done, until CX becomes 0. So it's like a loop, with the loop counter being CX. Now after each string operation, remember we're talking about in the case of bytes, a whole bunch of bytes in basically an array. Like that. After each of these string operations, CX is decremented. The 0 flag is tested, and if the answer to that test comes out 0, it quits. Okay. Now there are 2 that I want to look at. One is this scan string. 4 byte. So what this does is it compares this B1, B2, etc. with some kind of byte, some single byte. Okay, and I'll tell you in a minute what that single byte is and where it goes. And then there's a condition here. In fact, in this case, there has to be a condition. And that condition also has to do with the 0 flag. And there are only two possibilities, 0 or not 0. Or another way of saying that is equal or not equal. So the way to read this instruction is repeat while either equal or not equal, scanning the string and quitting if CX becomes 0. Okay, so there are actually two conditions in this one. There are two ways to quit. The first way is that this test on the 0 flag, which is condition here, which has to do with whatever the byte being tested against is. If that condition becomes true, it'll quit, whatever that condition might be. And the second case is the one I want to look at in this lesson, is a move string byte. B here stands for byte. It doesn't have to be bytes, it can be 2 bytes or 4 bytes. And here you can type the condition in, but it doesn't matter. It only cares about CX. That's why I have a condition is ignored. So you could type it in if you like. But you'll see, and I'll show you in the debug program, that it compiles to exactly the same instruction. Okay, so now here are the other, just quickly, some other ones. There's compare, and you might wonder why have a compare when you got a compare here. Well, this is not a comparison against a single byte. This is a comparison of a string byte against another string byte. So that's like comparing the values of elements in one string with the values of elements in another string. This I just told you about. This is stow means store. So to store something somewhere, and load means to read. Load. All of these things, the ones that I'm going to group these three, all these three ones, have to do with the accumulator. Okay? And that the accumulator is either AL, AX, and I'm not sure about the double word one. I haven't used it, so I forget. Probably DX, AX. It's always DX and AX tend to go together. These ones with source and def string operations. These are string and byte type operations, and these are string and string type operations. And all of these ones, you should add to this, and DI. Well, I'll leave it like that. So there's also this DI, which is an index into a string. And these ones have to do with the two registers SI and DI. These are called indices. This is usually always given the name source index, and this is always called destination index. Okay? Alright. So vaguely, now you have an idea of what's going on. So there are the two possible conditions. One might depend on the instruction, like that scanning a string. That's a single byte comparison while going through a string. And whether or not CX becomes 0. Now, you're going to see later on that the incrementing and decrementing of CX, DI, and SI happens every time through the loop. So even when the condition fails, that is when it's breaking out, there will be an increment or decrement of the DIs and the SIs, and a decrement of CX, always. Well, I shouldn't say always. When CX is 0, it quits. But whatever SI and DI are, when CX is determined to be 0, they will already have been updated by that time. Well, I'll show you by example that case. Okay, so just reading this through. In English, what this says is repeat while 0 or while equal scan string byte. Okay? So repeat while the 0 flag is set, but what's not being set here, and which is taken for granted, and while CX is not equal to 0. So CX is never 0 during the loop. So what does it do? It compares the byte at DI with what's in the accumulator. In this case, if it's a byte, a row, and then increments or decrements DI according to the value of the direction flag. The direction flag is set. DI decreases, it decrements. If the direction flag is unset, it increments. You're moving ahead in memory. Okay. And CX gets decremented on every time through the loop. So 3 things happen. A comparison occurs with DI and ALO. DI gets incremented or decremented depending on a flag. CX goes down 1. In the move case, a byte is copied from byte at position SI to position DI, which is equivalent of this move. Now I've got segment values written here because in actual fact it uses different segments for the move, but in our case the segments are all the same, so it doesn't matter. We can write it to our COM program. We're moving into destination from source. Now, this is not a legal instruction, but that's what the effect of it is. Okay, and then changing both SI and DI while it advances through the string. Alright, I'm going to pause for myself here and be right back. Okay, now I can do a little parallel processing here actually. First, if I go over to here, I want to test these instructions. Where they go. These two in particular. And that's what I got up here. I don't need any of that. I'm going to make a test program using my build system. Our program entry point is always 100, main we'll call it. And we would like to look at some data, which I'll call data. And I'll put that far away at 500, let's say. Here's our program entry point. Let me just start off with a quit. Now to get the data part, the easiest thing to do is another box. Use the debug program and fill up some memory with 0. And use the enter feature to enter in some string data. Oops. I have to say where. Under okay. Now I'm going to take this entire block of data, 80 hex bytes, copy it into my program, including the little descriptive bit, which could be useful. Now what I don't want are those dashes. I'll get rid of those. And in order to turn this into something the debug program can use, I put a db in front. That's the command that allows you to just start entering bytes. And indent that. And these here at the end are just comments. So I can put semicolon. Actually, make it slightly more closer to the other side. There we go. Now this here, what I've got, using the build system I've made, should compile. And there are some things that I don't handle automatically, and one is the entering of the code is just done in the order that they appear in the file, and that's important because the size of the file depends on which code is entered in last. So if I switch to the main here in this data, then we're going to lose the data. We've got to put the furthest in memory last, at least for the initial build. That linking thing doesn't care about that. Okay, now here's the result of our compiling, and see, it's this thing here. This is the symbol that means end of file. It has to appear as far enough away in memory to include all of the program. That's why if it started assembling at 100 next, it would have put an end of file following this int 20, and that would have been bad. Anyway, we now have a program. It's an object file, but it actually is ready to run because we have an instruction at 100. But I can debug an object file. And here's our int 20, and these are int 3. So if you remember, CC int 3 is a breakpoint. And the reason I fill this up with CCs is so that if some mistake occurs and we wind up at a bad address, then that's going to kick us back into the debugger if we're debugging it. So if I press go and we made a mistake and we land up in no man's land, that'll bring us back into the debugger and hopefully we can figure out what went wrong. Here's the memory. On at 500 we should have our data. And there it is. Okay. And further on, nothing. So that's what we intended to have. And now what I'd like to do is test out one of those instructions. And what I'd like to do is answer this question. How long is the string? And we can use the first one, SCASB, for that. Because if we put a value in alo equal to 0 and scan this string until the condition of the byte read from the string being equal to 0 becomes true, then if it quits on that basis, then we will find out how long the string is. So this is like Sterling. So how do we do that? Well, we might still want that quit at the end. First thing to do is to put the byte we want to test against into the alo register. Now, I'll just use a move, even though it's not the most efficient. 0. This could be any byte. Maybe it's a string. Maybe we're looking for a substring and we want to quit when we hit the letter S or something. Okay. Now, we need to remember, go back to this thing here. CX, if CX becomes 0, it's going to quit scanning. So in our case, since we know it's null terminated already, we want to make sure that CX does not become 0. So what we'll do is we'll set CX to a big number, the biggest possible number, by ORing it with FFFF. That's the same as move. Alright, it's easy instructions. So we'll put FFFF into CX, and there's no possibility of the CX becoming 0 and killing the loop on us. Okay, now what else? DI is the position where the string is that we're scanning through, which is data. So that's what we have to put in DI. Okay. Now, are we ready to go? We got DI, CX is infinity, the direction flag. Are we going up in memory or down? Well, we want to increment, so we want it unset, so we have to clear it. We have to clear the direction flag, and now I believe that we are ready. Repeat. Now, what is our condition? A-low is 0, and we want this thing to quit when it reads 0 from the string. So we want, if it reads this byte, say, and compares it against 0, and that condition is a true condition, then it's going to quit. If it compares it against 0 and that's a false condition, it's going to continue. So we want to repeat while the comparison is false, so while they're not equal, which is the same as saying not 0. And it's the scan string byte. And by the time this thing quits, DI will be pointing either here or here. That's the part initially that we don't know about. And if we wanted to determine the length of the string, we can determine it by just examining what the result of DI is and subtracting where we started from. Okay, so let's just see what happens with this. Okay, compiled. There's our code. Here are our registers. I'm going to run through the code. A-low is 0, didn't matter. CX is now infinity. DI now is at the position 500. String is, whoops, I just ran through this one by accident. No, I didn't. I did not, sorry. Clear the direction flag. It's already cleared. Usually is. Now this is sort of two instructions. Although, as I said before, the ref is like a prefix. But we can step through it one at a time and watch what happens. Well, it's not quitting, that's good. DI is going up, so it's moving 0, 1, 2, 3. And CX is going down. But there's no way this is ever going to hit 0. You know, we can't possibly put any number bigger than FFFF into DI. Okay, so we trace through a few of them. Now I can just proceed and it'll continue all the way to the end of the loop. Now it's done. And the answer we got back is 52B. Okay, well at 52B, here's 528. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B. So DI points one beyond the position where the test failed. And in fact, that's actually more useful than returning this position, it turns out, as you'll see in a minute. So the actual length of this string then, if we want to compute it, would be DI minus 1 minus 500. So suppose we want to compute the length of the string. I don't want to touch the bottom. No, I'll put that in AX. And I'll subtract from AX the initial pointer, data. Data here is just a pointer, a position in memory, 500. Okay, so we start out at 852B it was, and then if I decrease AX by 1, that is the length of the string. Okay, so now we've written the function stirlang pretty much. Okay. Now, so what is that value? Let's make sure that it's correct. Alright, let's compile this one. Trade, seed, trade, 2A. $42. Now, does that make sense? Let's look at our picture. Each of these lines is 16. So 16 plus 16 is 32. And here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it is in fact, the length is in fact 42. Okay, next thing is this is the multitasking part. Going through learning the instruction and learning the code at the same time. Suppose I want to copy this string somewhere to another position. I'll give it a name too. Data 1. 600, let's say. I'm not going to fill it up with anything. It'll just be CCs. For that one, we can use the other instruction I wanted to show you. MOVSB. So what we would like to do is repeat copying bytes from SI to DI while CX is not 0. I got these right now? Okay. So what do we want? We want to put a value in CX related to the length of the string. But which value would we like to put into CX? I would say that we would like to copy all the string bytes, but maybe plus the terminator. See? And that's why DI, as it is a better value than the string length to use for our counter, because that'll include the terminator. But in fact, before, well, okay, this is fine. DI. But we need to now put DI, which used to be a destination kind of thing, as a source. We're going to copy out from SI. Okay, so I could have put CX here if I wanted. Anyway, and we need to put into the destination our new location, data 1. Now we have our counter. The direction flag is the same as it was, and this other repeat only has one condition to stop, and that's when CX becomes 0. Okay? And the reason I don't like putting this here is because it's a little bit confusing. But anyway. Oh yes. This is not correct. We need SI to be equal to data. We want to copy from data here to data 1. It's at 600. It's not even included in our program, but that's fine. So SI is 500, DI is 600, and the count, well, that's wrong. See, that's why that was wrong. I forgot to subtract from CS data to get the string line, to get just the count of bytes, not the position. CX is more related to AX. This reads better. How about that? So move, put string len into counter, decrement to include no terminator, and now we want to do the move. So repeat. We're moving bytes. Now, in fact, that's all there is to the string copy. So now we've invented stir copy. If you can combine these two, you have stir copy. So, we're building our CRT run library, runtime library. It would be nice if we could print out the string, or print out how long it is, but we'll do that. That'll be added in a minute. First, let's verify that this works. Okay, compiled fine. Okay, here's our code, as you can see. Now at 500 is our string. We're going to find its length, and at 600 there's nothing, just CC. And after that move, this same string should appear here plus one extra 0 because we incremented CX here, the counter. So let's trace through it. Now we've traced through this bit before. We got the string length. Now we put that into CX, and we put it back to 2B. Now the source here we want to be data. And why would that 5001 here? Should be 600. Oh, that's one of those things. It's one of those things. This is why they put underscores, I think, in front of names. The search replacer replaced the word data, and it got mixed up because these two words are similar. Okay, how about this? I'll give them completely different names. Here we go. So we can keep this as it was. And there's no data 1, there's destination. I probably had an error and I didn't even realize it. Oh, yeah, I do have an error. Underscore 500. Okay, no errors this time. Now it's correct. 600. Trace through again. So we compute the string length, put that into CX, add 1, source index 500, destination will be 600. And I'm going to dump 600 out and show you again that it's really all C's. And I'm going to proceed through this repeated move. It should take stuff from source to dest and copy exactly 2B worth of bytes. I'm going to dump 600 again. And there it is. So it did what we expected, copied all those bytes, included the null terminator. So now we have strlen and stir copy. So we're building our runtime library at the same time as learning about these very efficient and useful single instructions. You don't have to have a loop and make up counters and do comparisons and all that. It's a single instruction. It does everything for you. I'll pause again for myself. Okay, 42 minutes. We're not doing too bad. So we've learned strlen, we've learned stir copy. By the way, we also have stir curve, I should say, which is the function that you call when you want to locate the first occurrence of a particular character in a string. Change that 0 to a letter like S here, and it would have returned, we would have been able to determine the position of this S by using the identical code. So in fact, strlen and span are the same function, exactly 100% the same function. The only difference is one uses 0 and the other would use a different character. Okay, so now we have strlen, stir copy. We also have memcopy and several other things probably from that. Just those two instructions. Okay. So now enough of my test.asm. And bring back to life okay, now this here, maybe log files. This here is pretty close to my first attempt at parsing a command line. And I think I showed you this before, part of it. And then we did an experiment and I showed you that there was something wrong with some of this code. In fact, it has to be changed. But there are some things that are right about it, and we can look at least at some cases where it succeeds, and then hopefully fix it completely. Now I called this parse command line. But that's probably not a good name for that. I could change that, and I might. I think I'd like to call this, tokenize, or tokenize, split into tokens, and this one happens to be based on the character 20. It reads through and it removes all spaces, and then the idea is that it's going to place the resulting strings in this storage area. That's why I call this argv store. It's the place where I'm storing the argvs passed into a program. CLP, shorthand for command line parser. These are just some comments. Probably remove that. Oh, actually, I put question marks in there because I couldn't do this before, but I fixed that in my compiler. I can put quotes now in comments. Okay, so this includes some of those functions, like strcur, memcopy, strlen. Now this strlen that I've written, if you look at it, because I realized what I just told you, I decided to allow a person to set the terminating character. So there's a special one character here that you can use as a terminator, and it has a named address. And so therefore you can use strlen, you could use strlen to determine the length of strings based on a different terminating character. In particular, the command line is terminated by a D, which is a line feed. Line feed, yes. I lost it. Now this strlen happens to use a stack frame, so you can pass it arguments on the stack. I didn't write it out, but I could put that here. So in the C declaration for this would be int, because it returns its value in AX. I'm going to do it like that, so to line things up evenly. Sorry, can't help myself. Int underscore, well, the C declaration doesn't include an underscore. And then normally it would be const car star. So that this function has that behavior. If you push a pointer on the stack, it retrieves the pointer from the stack and does one of these repeat scanning string. And what it puts in A low is what it finds at, this is not right, this would be that. I found a bug. Oh no, that is right, sorry. I did not, I almost added a bug. Strlen minus 1 is this position, stir term card. I could have written that here in here as well, but I gave this a label later on. Then to retrieve the value that's stored at this address, you have to put brackets. So strlen minus 1 is a pointer, put brackets around a pointer, you get the value, and it should be at 0. Okay. As far as other CRT type functions, this has a print a string. It uses strlen to determine how many characters to print. It doesn't examine the determining character. So for instance, if you wanted to print out a string that was within a string that had spaces in it, like a command line, and you knew that where the start of the string was, you could call putS and set the terminating character to space, and then it would print out that substring in the command line. Now it's comparing. Now it's checking to see if the length is 0. If so, it's going to go to finish, clean up. Otherwise, into CX goes AX, into BX goes BP plus 4, which is the string passed into this function, the value, then the value of that is a pointer, and then it's doing printing character by character by putting into dlow the character pointed to by BX and pointed at by BX, a high 2 and int 21. If you recall from our 2-upper program, that's that combination prints to standard out, and then incrementing BX and looping. Unfortunately, in this case, can't use the SCASB thing because that's not, calling int 21 is not something that you can use the rep with. Now this loop thing also has to do with CX, and it quits after CX times through this loop. That is, if at this point CX is 1, if CX is 1 here, just before the loop instruction, then it'll quit. That is, it'll decrement CX. Check the 0 flag. If the 0 flag says 0, it quits. Now, you can see why that's true, why that's the valid thing. Just imagine CX is 1, meaning that you only want to print out one character. It comes through here, CX is 1, and it would fall through. So therefore, that's the correct behavior. You don't want it to loop and print another character when you've specified a length of 1. So that actually will print the proper amount. Memcopy we looked at before. That uses the move that we just looked at. Stircar, as I said, yeah, well, see, this stircar is a little bit more thorough than what I was saying, because it might not be, the string might not have that, may or may not contain the character we're searching for. And in that case, the rep scan combination may quit on the basis of the fact that it hit the end of the string. Or it may quit on the basis of the fact that it found the character we're looking for. So when it does quit, and if CX happens to be 0, then there are two possibilities. One, it quit because CX became 0, or 2, it quit because, well, the other condition might still be that the last character examined was in fact the character we were looking for. So that's why at the end here there's an extra test to see. Here's the final comparison. Was the last character just before I quit, was that a C passed in? C is passed in here as a second parameter for this function. So there's an extra test there. Okay, fine. Now I've tested these functions and I believe they are correct. So now I'm going up to the parsing bit. Now, maybe I should just give an outline of what I want to do. Yeah, so that means I should pause and think of the best way to word it. Hello again, back again. I've given it some thought, and I think I have a good way to explain this process speedily. And I've written down first how you would write this declaration in C. Although it's not, here's the function. There's a subtraction of 6 here. That means I'm allocating 3 ints on the stack. Now this one here, the BP minus 2, would be in memory, would be the furthest along in memory. That is, it's closer to, it's more closer to the end than to the beginning. So, actually I've got it written here too. This bytes remaining would be, in fact, the last thing in this list of 3 in. Okay. Then BP minus 4, I was making these up as I went along, is where I stored the position of the final carriage line feed, should say. Line feed. I always get them backwards. Yeah, I was running out of registers, and so I started eating up the stack. And then I realized I needed to save another thing, and that minus 6 one, which is actually would be the first one in that list. That's a position, a current position in this big data table that's going to contain the final result. Okay, so as we're saving them off, I'm saving, just keeping up, updating this position where to save the next string, if there is a next string. So here's here are the steps. First, check for empty conditions and things like that. Set up any variables, max length, and so on. So then it really starts here on step 3. So find the first non-space. Save it off. Did we hit the end? If we hit the end, then quit. That means the whole thing was spaces, and there's nothing left to do but quit. Nothing more to add. Now that we found if that's not true, then we did find a non-space, and we know where it is. So now we scan forward for the next space for line feed. Line feed is the end of the buffer. And then we save off all bytes between where we started and wherever that next space or line feed is, not including those characters. Now, if we did hit the line feed, we're done. Otherwise, we go back to step 3 and repeat until we quit. So that's basically all there is to this program. Now I'm going to compile it, and even though I've noticed several mistakes in the way I've done this, I'm going to keep this here. In fact, I'm going to do it on this side. I do want to save that. Okay. I'm not sure. I don't even know which one it's asking about. Okay, so here we have my prog. Okay, that is what I wanted to see. My prog, and I'm going to compile it, and we have the code in the other box, so we can refer back to this box for whatever they need. So let it compile. Now this one should be okay. I haven't touched it. I didn't move anything or add any new lines, so everything should be properly lined up. And then, of course, I'm going to have to fix it because there are several mistakes, and there's something I need to check too, which I'll get to while we're stepping through the. I'll do let's say well, the empty case first. That'll take 2 seconds. Okay, it's compiled. We'll do the empty case, and then we'll do a single word case, maybe with some spaces on in front and afterwards, and then maybe 2 words. In fact, there are only a few cases, and the thing that you're going to find out, and what I believe is true, is that if we nail this problem, this simplest case problem, then we've nailed it all, because of this trick that I discovered. Okay, so as long as these numbers match up, it's okay. You don't want things overlapping, so that's okay. And sometimes things have gaps in them. There's a gap here, but this is an intentional gap. I left a space here because I thought I'd be putting a lot more parsing code in here. But now I believe that just this one function, if it's solid, it can cover everything. And the trick is something that you can only really do in DOS. You can't do the trick that I have as easily anyway in Windows. Okay, these are separate functions, so they all have their own special addresses. This is the same function but lines up. These are labels. This one's completed. This is another function. Which one is that? Oh, that's that wrong mem copy I mentioned before. It's restoring AX back to where it started as. Okay. Okay. Everything looks good. All right. Okay. Now this has to be actually a COM file, and I have a batch file called G, where I set up my experiments, and this is the first test, I'm going to try this thing, this batch file. It just does some renaming and deletes some garbage. Okay, so this should start it up with no arguments. So here we are. There's a call and a call. What's the second call? Oh, main. The main would be where the user would have place their code. So I added that at the bottom here. Just returns. So 500 is our function. Parse command line 500. Trace into there. And now we are here. This is where we are. I can't have them both on the screen at the same time, unfortunately. I can sort of have them both on the same screen. I could resize that, and then if we need to look at the two together, we can see it. Okay. But for now, we'll leave it. Okay, so now set up the stack frame, allocate 3 ints. Now I'm using the A high and B high and C high. I want those to be clear. And the reason I want those to be clear is because basically the PSP, okay, is 100 bytes, okay. So that means I can address any byte in the PSP with a single character, because it goes from 0 to FF. And in our case, we're only going from 80 to possibly to FF. So I'm working with the high and low registers. That gives me double the number of registers that I would normally get. Instead of 4 registers, I got 8. So these pointers are actually mini pointers that only have a range of 100 bytes. But that's all we need in this case, because the full range of this thing is 100 bytes. In fact, all we care about is this bit. So, but you can't break a register into another half or anything. Okay, so that's why I want these clear, just so I can either use them for transferring or swapping some data or something, or I might want to use an indexing thing, and I want to be sure that the whole thing sometimes might evaluate. I want it to evaluate to just the low value. Well, we'll see that when it comes up. Anyway, where are we? So move into A low 80. That's supposed to give us this one, which will tell us how many program arguments there are, and this should just quit immediately. Trace, check if it's 0. If it's not 0, go to 516. Now this is that weirdo code. This leave thing is too far away for a regular comparison jump. Jump if 0 to leave. And I didn't want to add a new label, so I just took the binary code for jump if it's not 0 over this jump. and it is 0, so now we're going to hit this jump to leave, and so I can do a long jump. But you know, it's kind of silly because it's easy. This is assembler. You can do anything you like here. You know, I could take this instruction, or this set of instructions, and put them here. You know, it doesn't have to be at the end. So, but anyway, you can do a lot of things in assembly that you're not allowed to do in a structured language. Like I can place a function inside this function. There's no problem with that. You know, no problem. Add a function. Anyway, so jump is not 0. That's not true. Now we jump to 640, which should be that leave thing. 640, which is this leave, and we're done. And then it would resume the program. This does nothing, so the 0 case works. Okay. So now let's go to a more complicated experiment. We're done with it, sort of done with it. Because I have to go through all these again after fixing it. I don't want to do this one yet. Let's just do single argument, no extra spaces, where the user had to press the space. Now I've been assuming that all along, and now I know that that's false. You don't have to have a space here. So that's what I have to change and fix. For instance, you know, this is valid. That's a valid command line. Program /A. And in that case, you don't have to have a space. There might even be some data here. You might not find a single space for the entire command line. And here I am trying to do spaces. But anyway, sometimes people do press space, and it's got to work for that case too. So let's try this one. We should get a single A. We'll maybe I'll use a little a. I'll have a little b, because I know that that's 62 hex. And okay, so let's see this. Let's see if this one works. Go. Okay, clearing out the registers. Now check. Now this time we have 2, so our command line contains 2 characters according to that. Now, according to my code here, this is something I thought was theoretically impossible, but anyway, I'm comparing with 2, and it was my belief that you had to have at least 2 to have anything on the command line. That's false. But in this case, we do get 2, so it's okay. I'll check the 0 case first. Not 0. Is it below 2? Yes. Now I'm taking 1 away from the count and storing that value in what I call bytes remaining. So that means that there are 1 bytes remaining on the command line besides the line feed. I'm saving it off, and I'm putting into AXD, which is a line feed, and what I'm doing with that line feed is I'm going to call stircur to find out where the position of the final line feed is. But actually, I should have used this stirlen. Well, actually, I don't have to call any function at all. If it's true that it's always line feed terminated, if there's always a D, I don't know that for sure because I haven't typed in a long enough command line, but if it's true that there's always a D, then this number plus this offset minus 1 should give you the position of the D. Okay, so if this is 0, just this position plus this number should give you the position of D. So let's see if that's true. This position plus this number 1, 2 is the position of the D, right? So this calculation is useless, but it's a good double check. There we are. So we're going to use stircur, push 82, our current position, assuming we're at position 82. That's here. You see, I kept thinking you have to have a space here, so I'm just discarding, not even thinking about this thought. But it is true in this case that there's no D here because this is not 0. And then I'm going to call stircur. Now I'm just going to proceed through stircur. That should tell me either I get a null if it can't find the D or an address. Now it says 83, 80, 81, 82, 83. That's correct. Store the stack. So we are now on this line. And I'm saving off the position of the D, 83, which we could have determined by taking this 81 and adding 2 to it. And saving it off, making a duplicate basically of this combination. So, I mean, it's not. When I first wrote this, I was just kind of writing it as I went along, and not thinking of the simpler ways to do things. Now, this BP minus 6 is the first thing in my list, the pointer into static data. So that's a position in the static data where we're going to put the arguments, copy the arguments there. And so I'm starting at 200, happens to be where this is. 200. Save it off. This is the only time it's initialized. And now I'm going to move. Well, what I'm doing now here is I'm setting the stirlen character to D. So that's another bug that's wrong. The terminating character for stirlen needs to have been set to D earlier than here. I think actually I can't fix that swear. See here we called stir curve unnecessarily anyway. And that stir curve uses stir length. But if there were no zeros, then it would have just, the stir length would have just kept walking through memory forever. So I should have, this line, whatever it is, putting the the string terminating character to line feed should have occurred earlier. And see, I've even written here, it's necessary to avoid a crash. It's necessary also for this. Alright, anyway. Now we go back to 82 again. Keep reminding you about this. Where we are here. 82 is this position. And now I'm going to search for a space. You see, this is a lot of extra work. It should be done by now. Look for a space. Is CX0? Yes. So we're done. Now jump to this. So what happens when CX is 0? Okay. Now we're jumping to check last character. We're going to check to see if the last character is a line feed or not. Right? Is that what we're doing? Following stir 20. Next we're oh, it's just copying the last argument. Is that what we're jumping to? That's not what we're jumping to. CX0 condition. Check last car. We're on this here. We retrieve position of the last line feed. Back up one. Check if it's a space. If it is a space, get out of here. Otherwise, BP minus 6 is a static story. And then we store the character. It'll have to be a single character. Yeah. Okay. I'm not even sure why that logic is correct. But I'm going to change all this. Pair with space. Not a space. Put that in the static storage. Oh no, get the value. A low, which is a 62, which is a little b, and put that into DI 200, the letter B that I typed in the command line. And now we're exiting. So it happened to turn out correctly in that case. Now lastly, hang on. One more experiment before it's done. Not a complicated one. So we've done that test. Let's just do this works with a single character. Let's just make, if I add one more character to this, we've covered all cases of just an immediate string following space. and then that part would be done. So let's try this one. Oops. What did I say? Goes here. So we should get AB this time. Okay, again. Here's our command line. 83 characters this time. Compare with 2. Take one away. That's the characters remaining on the command line. This is the unnecessary scan for our. I've jumped into one of the runtime functions. Well, this is stir scan. Stir curve. And then get out of this. Okay, it's getting out. And the answer is 84, which is supposed to be. It's supposed to be the position of the final D, which is this plus 3. And that's correct. Well, it's a good double check anyway. Save off static storage location. This line is saving off our current position. What is it? What's the middle one? Oh, those are the final D. That was 84. Static storage saved off. Change string when terminating. Go to position 82. Scan for a space. Put into CXD. That's the count of characters remaining. And CX0. No, it's a 1. Add 1 to CX. And the reason for that is explained in the comments here. It's because of this SCASB. There's a post decrement. So CX is always 1 off after it's SCASB. So whether it's a position of the line feed or the space we were scanning for, that CX is going to be pointing 1 beyond it. That CX counter, I should say, would have decremented once too much, and the search pointer would be 1 too big, and that one therefore has to be decremented by 1, which it is. So basically we're back to where we started. And now putting space on the stack, we're calling stir curve for space, and we get null back. There is no space. So count is not 0, but it is 0. That's this here. So that means, if null, that means we hit the line feed. So we just copy all remaining bytes. Okay, and there are 2 remaining bytes. Now we're going to call memcopy. We load into AX our current position in the static data. Push, call memcopy. First we push the count. Memcopy takes 2 arguments, count and string value. Push in reverse order. Call memcopy. jump 200. There's our AB. Jump 2. We're done, and we're done. So there are two cases done. So the case of immediate string following a space has been completed. Then I add one space to the beginning, then I add some spaces at the end, then I add spaces in the middle, and that covers all possible cases of spaces in 3 more experiments, if there's a space following on the command line. And once every single case is covered, then I'm going to show you the thing that I discovered, the method that I discovered, which I think should be enough to pretty much nail the whole thing all in one go. Just if this thing works perfectly, we can do all the rest with a trick. Okay, see you then.